All right, so welcome to the third lecture of GPU programming. Uh, and we looked at computation, we looked at memory, and then now today we are going to look at synchronization. Right. So briefly, we did start thinking about synchronization as we looked at some aspects related to sync threads yesterday. But let's look at it more carefully today. Um, and synchronization turns out to be one of the interesting aspects while dealing with parallel programming, more so on the GPU. Also, it's a little involved, so I request all of you to pay attention while we are going through the slides and ask questions. So let's first define what is meant by a data race. We say that a data race occurs if all of these conditions hold, right? So there are four such conditions. One is, of course, there should be multiple threads. With a single thread, a data race cannot occur. They all should be processing the same memory location, right? That is another expectation. At least one of them should be a write, which means that all read-only operations do not cause a data race. And then there should be a concurrent execution, that is simultaneous execution of these threads. If they are occurring or spaced out in time, then the data race will not occur. So as long as these conditions are satisfied, that means that the data race holds. And what that also indicates is that since all of these are necessary conditions, even if you falsify one of them, the data race will not occur. Right? For example, if you separate out the memory accesses to this common memory location in time, and you ensure that they don't occur simultaneously, then essentially there won't be a data race. Right? So like that, we might have to devise different mechanisms, right? So such mechanisms do exist. For example, I might just run part of that code where the data race exists sequentially, right? So, and that will ensure that there is no data race. Instead of a common memory location, I might create copies of that common memory location, do something independently, which is called as data privatization. And then finally, using another mechanism, merge these results, which are locally manipulated. I can also separate the reads and the writes by a barrier, and what that ensures is that the one phase becomes read only, right? The other phase might have, if it's a single write, then there is no problem. If there are multiple writes, there is still a data race, but hopefully multiple writes you will be able to take care of in a different way. And we can, of course, create locks or use atomics to ensure that there is mutual exclusion. That is, the different threads do not access the same memory location at the same time, right? So that is what is our usual locking mechanism from the operating system, right? So the way we use mutual exclusion is that we say that there is a common memory location. I lock it. That means that every thread which wants to perform an operation on this common memory location, it needs to acquire that lock. Only one of them is guaranteed to get the lock. That is the semantics of the exclusion lock. So only one thread gets the lock. That thread enters, this is called as a critical section, enters the critical section and performs some operation onto the shared data item. And after that operation is done, unlocks it, so that other threads which are interested in locking it, one of them will get it, and so on. This keeps on happening depending upon the use case. Now, this ensures that only one thread is in the critical section at any point in time, right? So this is something which you would have probably seen. Maybe if you go to some RTO or some other office, maybe government office, right? So there is a clerk sitting inside and only one person is allowed to go inside, right? So at the gate, the security guard is going to stop everybody, right? So that stopping is essentially you're trying to acquire a lock. Only one person goes inside, and after that person comes out, then the security guard allows the next person to go in, right? Or even pandemic time, we used to encounter such situations. So locking mechanism is quite similar to this, and we would like to implement such locking protocols as we go along. Okay. Let's do a simple exercise, right? So what we have are two threads, T1 and T2. There is a shared variable flag, right? And the code of T1 and T2 is shown here, right? So flag equal to 1, while flag do nothing, And if flag is false, then execute some statement S1 which doesn't change flag. The T2 says while flag is false, you wait, and as soon as it becomes true, execute S2 and then set flag to 0. The question is, what does this code achieve? Any suggestions? Okay, let's solve the simpler question first, right? So the simpler question is it possible that S1 and S2 execute simultaneously? So in another way, we are asking if there is mutual exclusion between T1 and T2 with respect to the critical section S1 and S2. So any thoughts on whether S1 and S2 can be executed in parallel or not? Please think about it.
Yes, they can execute in parallel if there is a context switch between T1 and T2. Say first T1 is scheduled and it sets flag to 1. Sorry, T2 execute first. It reads the initially flag is 0. It will set the while condition to true. And it will come out. No, just a moment. Okay, yeah. T1 execute flag equal to 1. And then it is descheduled. Then T2 executes. So the flag value is 1. So it will go on. It will come out of loop and T2 or T1.
Sure. So I request, the way Vipin was thinking, I request everyone to also think in a similar manner, and we'll discuss. See, the synchronization protocols are a little complex, and we need to worry about large number of different interleavings. The way, for example, Vipin was suggesting, maybe initially the value of flag we don't know, so it could be 0 or 1. Assume that it's a Boolean value, and then which statement occurs first, or even what is the initial value. That all those combinations will start coming into picture, right? So therefore, although the code is small and we might be able to actually enumerate all these different possibilities, it's important to do that exercise. Okay, so let's take both the initial values, right? So some of you are suggesting that Sandeep, Bhagavan, Sowmeya, Pirapuraj are suggesting that the mutual exclusion is guaranteed. That is, S1 and S2 will not execute in parallel, right? I would like you to also keep thinking about what does the code do, right? What does it ensure? Chinmay says T2 while condition becomes true if initially flag is 0. T2 while condition becomes true if initially flag is 0. Okay. Then the context switch to T1, which makes T1 while true. So both can work in parallel. I see. Okay, so let's understand that. Okay, Soumik says at the assembly level, both can work in parallel if we think about it that way. So initially, if the flag is 0, then the while condition can be false. Sorry, the while condition will be true. And if that is true, then T2 will be stuck in the loop. Does that seem reasonable, Chinmay? Okay, so let's discuss that, right? So if flag is 0, while not of flag is 1, and therefore the T2 is stuck in the while, so it cannot go to S2. Okay. Let me take Soumik's suggestion. As T1 before writing can context switch, and T2 can go inside, and then T1 context switches back. So T1 before writing meaning before writing to the flag, I suppose. Context switch and T2 can go inside. So if T2 has gone inside, that does mean that the flag is true, right? The flag has become 1. Right? If flag has become 1, then that flag equal to 1 is either coming from the initial value or T1 has executed that. Right? Irrespective of what happens, T1 cannot go outside the while. Does that seem reasonable? Show me. Okay. Any other? Yeah, so Chinmay, after we are in loop for T2, we switch to T1, okay, which makes the flag 1. Sure. And we enter into T1's loop. That is correct. We will enter T1's loop, but we will not be able to execute S1 and S2. Right. So this while loop is not part of the critical section. The while loop is kind of waiting at the door in a shop. Right. So you have not allowed to enter. When you enter, then you execute S1 and S2. Right. So S1 and S2 are the important parts. The while loop is essentially blocking. Sandeep says T1 may loop infinitely and S1 may not execute always. That is a good observation. Why would that happen?
Sir, because if flag 0 is executed and then flag is equal to 1 is set by T1, then T1 is going to loop.
Right. So if so let's understand what Sandeep is saying. Right. So why would T1 execute infinitely often? Right. That is, it is stuck inside that while loop. The reason is that it is expecting flag to become 0, but that never happens. And why would that never happen? T2 is there. I mean, one possibility is that maybe T2 is not there at all, right? So that is another possibility. But let's say T2 is there, but it got executed prior before T1 began its execution. So T2 executed because maybe initially the flag value is uh, 0. Flag value is 1, and therefore while not of flag is 0, and therefore it came out and started executing S2. Right? And then it set flag equal to 0, right, for thread 1 to execute. So let's say thread 1 starts executing after flag equal to 0, then flag becomes 1, and then while flag it's just waiting. Is it possible that T2 gets stuck in presence of T1? I mean, T1 executes at some point in time, but is it possible that T2 gets stuck? We said that T1 might get stuck, but is it possible that T2 might get stuck in the while? Again, we can take both the values 0, 1, and T1 executes at different places and so on. Okay, so let's understand that, right? So we'll come back to our original question of whether S1 and S2 execute in a mutually exclusive manner, as well as what does this code do. But let's take the flip side of what Sandeep was saying. Can T2 get stuck? So let's say that initially flag is 0. Then while not of flag is true, and therefore T2 is actually stuck here. But then we said that T1 can execute at some point in time. Right? So we don't know how much time it will require, but there is some finite amount of time that it will take. At some point in time, it is going to set flag to 1. And if that happens, then T1 is waiting, but T2 can proceed. Now, isn't it possible that T1 has executed already? Right? So if it has executed already, then it has actually set flag to 1. And if that is the case, then this condition will be false and therefore S2 will execute. Third case is that initially the value of flag is 1 actually. In that case, again this condition is false and S2 gets executed. If initially flag value is 1 and it gets overwritten by T1, still the flag value will be 1 and therefore S2 will get executed, right? So therefore T2 doesn't get stuck in any execution. So that is essentially coming to what this code is doing. But irrespective of what we try, it's guaranteed that S1 and S2 do not execute simultaneously. It's possible that S1 may never get executed. That we discussed, as Sandeep was suggesting. S1 may never get executed, but S1 and S2 cannot execute simultaneously. And one of the reasons this happens is because of dependence on a single variable, which is always going to have a single value, either 0 or 1. There is nothing in between. Right? So it doesn't happen that two threads see two different values of flag simultaneously. They will always see the same value, right? That is our expectation. Although in reality, that is not true. Right? So is it possible that there is a shared variable like flag and two threads see different values of that flag? Is it possible? Any thoughts on that?
Sir, please repeat the question.
Yeah, the question is it possible that flag is a shared variable, right? In this case, is it possible that two threads see different values of flag at the same time? Sandeep says no, if no cache coherence problem. Okay, Pirapuraj also says no. Yeah, so this leads to this cache coherence issue, right? And if that cache coherence is not properly, well, if cache coherence is not implemented, then it's possible that they might see different values. So here the expectation is that different threads are working on different cores. Each core has its own L1 cache. And therefore, when one thread, right, so when one thread is writing to the flag, let's say initially the flag is 0 and one thread is writing to the flag and another thread is reading from the flag. That write has to ensure that the flag value is invalidated and updated at the common memory. That common memory could be L2, L3, or it could be DRAM. And it should get invalidated in the other cache so that the other thread sees the modified value. So if this is not implemented in this particular manner, then it's possible that you might update in your local cache L1, right? It might not get invalidated, and then thread 2 can see the old value 0, whereas thread 1 is seeing the new value 1. So more often than not, this does happen in the sense that in the real hardware setting, right, on GPUs, on CPUs in parallel programming, it can be, in fact, you will encounter this, that you will update from one thread and that update will not be visible to the other threads unless you as a programmer do something extra. So Abhishek says, can cache coherence issue be seen by the programmer? If it is implemented properly, the way we study in textbooks, then we will not be able to see it unless we work at the architectural level. But you will see it in this particular course if you implement even this simple program. Chinmay says, in assembler level, we may read and other second process after context switch one would have updated till the time we are checking condition on the flag for the first process. So can you, so yeah, so that is fine, right? So for example, you might read the value which is for T1. Oh, okay. Sure. So irrespective of whether the cache coherence is implemented correctly or not, in this particular program, there won't be any mutual exclusion violation. Right? Vipin, you have a question? Okay, I'm not able to hear Vipin. Sandeep, go ahead.
Sir, you were saying that if some thread changes the value and that may not be reflected in, so that is a cache coherence problem, right? But in my PC, if I take my PC, that will be handling cache coherence problem, though there is an overhead of time, but it will update all the, I think it will update all the location, I think this, to put it in a simple way, I think there is no cache coherence, sorry, there is no problem of cache coherence, I guess, because you were saying that
It will be there, is what I understand. And most probably you will encounter it when you try to implement it in this manner. And the reason being that many of these programs, for this reason, suggest that they are going to support something called as a weak consistency. And that means that until we explicitly ensure that we are reading the value from a common memory location and writing the value to a common memory location, it is not guaranteed that the write from one thread is going to be visible to the other. Right? So, but anyway, I think instead of believing me, it might be best to check it out that this actually is happening, right? And we'll see some of those programs as we go along. Okay, so with that, let's understand this. So yeah, so one question is there a data race in this? Right, so any suggestion? Okay, Vipin has a question. Meanwhile, you can think about this question. So if the flag variable is allocated in the register, then both cores may see different values of the flag. The registers are out of scope of the cache coherence protocol. That is correct. That is correct. That's a good point, actually. If it's in the register, yeah, so maybe I don't know if that is the thing that is happening here. The reason being that so let's say that you are writing to flag, right? And you will write to the register. That part is okay, but you also need an instruction to move the memory move the value from register to the memory. Now, this update needs to be reflected at some point in time, right? So you are saying that if it is in the register but it has not been updated in the cache also, will that be possible? Yes, it's possible in an optimized program, and that's one of the reasons why we would like to disable these memory related optimizations when we are dealing with these common shared memory locations, right? And that is where we use volatile, in which case you will not keep the value in the register, but you will ensure that it gets pushed, right, before proceeding further. Yeah, but I don't know if that is the only place. So, but yes, I agree that this definitely can happen with an optimized program. And the program, it becomes programmer's onus to specify something more to ensure that the value that is written by one thread is actually accessible to the other threads. Okay, we'll discuss more on this anyway. We have a lot of things to cover. So is there a data race in this particular code according to our definition? Any thoughts? Okay, Pirapuraj says no. Sandeep says yes. Abhishek, yes. Vipin, yes. Okay, so okay, Satya Bhagwan.
But that concurrent access is missing here, right, sir?
Okay, so let's understand this, right? So let's take even the first statements of both the threads, right? So we said that there are a flag equal to 1 and while not of flag, which means that there is a reading happening from T2 and there is a writing happening from T1, right? Is this simultaneous? Is it possible that T2 reads the value of flag and T1 writes the value of flag simultaneously? That seems to be possible, right? Although there are some additional things which I'll skip, but in the sense that there is no garbling of bit patterns that is happening. So therefore, there is a possibility that at the same time, at the assembly instruction level, we can see that flag might be read by one thread and flag might be written to by the other thread. It's a common memory location. There are multiple threads, simultaneous execution. And therefore, there is a data race happening in this program. Data race doesn't necessarily mean that the program output will be wrong. Although many of the languages, parallel programming languages, do not give guarantees when it's a data racey program. So they require data race freedom to ensure that certain guarantees are maintained. In this case, there is a data race, but the data race is inevitable in almost all the locking protocols because one thread might be actually reading that value in a while loop and the other thread might end up writing to it around the same time, maybe for unlocking, and therefore there is a data race that way. Thankfully, it so happens that for primitive types like integer, character, float, double, for primitive types, the access is atomic. What that means is that you are never going to see half-cooked byte pattern out of this primitive type, in this case word, right? So assume that flag is a Boolean value or a word value, integer value, and you will never see half-cooked bit pattern. That is, if you are writing, let's say hexadecimal AABBCCDD, right? You are writing hexadecimal AABBCCDD, and the original value of that variable, shared variable, is 0. It will never happen that you will see AABB00 or 00CCDD like that, right? So that is what I am saying. So that primitive type access is always atomic, which means that you will see either the 0 value or AABBCCDD value, the new value. So that is where, if you go to that level, then you might say that, oh, then there is, it's not really happening simultaneously and therefore there is no data race. But we will maintain it at the assembly language level and we'll avoid this particular aspect. So the writing to flag is atomic, but we'll still say that there is a data race in this program. Okay, so the code ensures that if the flag is initially 0, then S2 executes before S1. This is the guarantee that it gives. If the flag is 0, then while not of flag is going to be true, and therefore the T2 is going to wait, and then T1 is going to set flag to 1 either now or before T2 starts executing, but the T1 is going to wait until T2 sets flag equal to 0 here, and therefore if initially the value of flag is 0, then S2 must execute before S1, right? So that is one guarantee that it gives. On the flip side, if the initial value of flag is 1, then S2 executes, that is guaranteed, and after that S1 may execute or T1 may hang, right? So the T1 may hang was the possibility that Sandeep was suggesting, but it is also possible that T1 might not hang, right? So depending upon at what time T1 got scheduled, right? So if it got scheduled after flag equal to 0, right? So then it will set flag equal to 1 and it will get stuck there. But if it does flag equal to 1 first and then flag equal to 0 happens by T2, then this particular condition will become false and S1 will start executing, right? So depending upon how the scheduling is, this is what the program is currently doing. Okay, so far we did not use any CUDA related aspects, right? So this is possible even in C parallel programs. So we'll slowly get into that, but for that we have to understand a little bit of mutual exclusion protocol. So we did it for 2 threads. Can mutual exclusion be generalized for n threads? Yes, it is possible. Just that instead of 1 flag, you might have to use maybe multiple flags. Sandeep says T1 may hang irrespective of initial flag value. So if the initial value is 0, T1 can still hang, is it?
Yes, sir, because maybe flag is equal to 0 got completed, and then after flag is equals to 1 may start, right? So addition, I think we have to add one more flag so that T1 doesn't stall.
I see. So, okay, let's understand this, right? So if flag is initially 0, then while not a flag is true for T2, and therefore T2 is waiting. I don't see that. Can you repeat? Maybe Sandeep or Shubham, can one of you explain that?
Sir, suppose flag is equal to 0 is set, is completed by the T2. Then after that, flag is equal to 1 is executed by T1. Then there is no chance that T1 will continue, right?
But why will T2 execute flag equal to 0?
Like if you take the case of flag is equal to 0 initial value,
Correct.
then okay, I will rethink.
Yeah. So if flag value is initially 0, then while not a flag is true, and therefore T2 is going to wait. Right? T2 is going to wait till flag becomes 1. And the only way flag can become 1 is either coming from initially or from T1. So therefore, it will never happen that flag equal to 0 will get overwritten with flag equal to 1 if initially the flag is. Does that seem reasonable, Sandeep and Shubham? Anyway, think about it. Maybe I am wrong, but think about it. If there is something wrong, we'll have to update the slide. Okay. So, yeah, so what we are going to do, well, this is essentially the histogramming work that we were discussing. So let's say that, and we'll come to the mutual exclusion part soon, but this is to give you some glimpse of where you will require synchronization, right? So if you have roll numbers and marks of, let's say, some 80 students in the GPU programming, and we want to assign grades, right? So let's say that I use this criteria. So we in IIT Madras, we have these grades called S, A, B, all the way up to E, and then U means a fail grade. So I set the cutoffs as 90, 80, 70, E equal to 40, and anything below 40 is U. So I am given the input arrays. Input arrays say that I am given roll number and the mark of that particular student, and I want to compute an output which is going to be the grade corresponding to each student. So that is one part, right? So how will you do this? Well, that seems to be easy. It's nicely parallel problem because I can have 80 threads, right? Each one is assigned, and then each thread checks if the value is appropriately. There is an if-else nested loop, nested conditions, and that is going to be directly computing the grade of each student and updating the output in parallel, right? So every student is processed parallel. Now the second thing that we want to do is to compute the histogram, something like this. Right? And yes, we don't want to really plot it, but we want those numbers that for every grade, how many students exist. How will you implement it from the perspective of achieving this particular target? That For each grade, I want to know how many times a student has come into that grade. Okay, so let's say that there are these 7 arrays available with me. Not 7 arrays; these are 7 grades available with me, and then there are 7 counters. Right, and I have another nested if-else statement. It says that if the grade is U, then update count of U plus plus. Right. Else, if the grade is E, then count of E plus plus, and so on, right? So I can have this nested if else statement. The question is that going to work, or are there any issues with it? I'm just going to write this read of TID equals U, then right. So this is the kind of statement that I'll be writing in my code, so that at the end I have all these 7 counters. Correct. So as we were discussing yesterday, this count U plus plus is not an atomic instruction. We are not taking a lock on something, updating count U and then releasing the lock. And therefore, it's possible, as Abhishek and Sandeep are suggesting, that some updates might get lost. Right, and we'll look at this particularly as we go along. So we require some sort of synchronization. Okay. Another example is to compute shortest path. So let's say that you are given an input graph of India, right, and you want to compute the shortest path from this city Nagpur to every other city. Why Nagpur? Well, not only because it's my native, but also because Nagpur is considered to be geographic center of India, right? So there is a notion called 0 mile inside Nagpur, right? So from where the directions are measured in the distances are measured in various directions. So anyway, so let's say that you want to compute that, right? And assume you are given a GPU graph library and the associated routines, and we want to settle the distances in Bellman-Ford style, right? So essentially, we have this as Nagpur, right? And then there are these distances, I mean the edges, the roads connecting different cities. And then we know that if A is at 0 distance, then B gets the distance 7, C gets the distance 3, and D gets the distance 2. And then when you settle this particular edge, at that time you check if the original distance, which is 3, is greater than this alternative distance coming via D. Right? So depending upon the edge weight CD or DC. And this you keep on doing it until all the distances are settled, and that is our shortest path distances. So the code for this might look like this, right? So I have single source shortest path, which takes a graph and then a distance vector, right? And I compute the thread ID. Each thread is operating on, let's say, one node. Right? So what I do is, for each of the neighbors, right, of that particular vertex, which is associated with the thread ID, right? So the number of threads is equal to number of vertices, right? So each thread is operating on a vertex, and I go over all the neighbors n of ID, and I compute the alternative distance, which is the distance of the source plus the edge weight. If this alternative distance is smaller than the current distance of the neighbor, then I update the distance of the neighbor. Right? So this is my shortest path computation. Ignore all of that, how to implement graph, etc. But this particular processing, do you see any problem? Okay, what is that, Sandeep?
Sir, if you consider this node C in the graph you gave, so there are for A and D, the common neighbor is C. But if you take the code which you have written, and for suppose A is executing the code and D is also executing the code, then actually the distance we don't know, like which distance will be put into the corresponding distance of C. I think the comparison should be in the atomic.
Okay, sure. So as Sandeep is suggesting, let's understand that, right? So let's say that this distance is actually 2 edge weight, right? And therefore we expect that whatever is the distance from A, that is 3 should be the distance of C from A. So that seems reasonable, but let's see whether the parallel processing allows this to happen. So there is one thread operating on A, another thread operating on D, and let's say the distance of D is set to 2 already. At this stage, both these threads, the one operating on A and the one operating on D, will try to write the modified distances. So what they will do, they will go over the neighbors, they will compute alternative distance, which is distance of A plus 3 and distance of D plus 2. So alternative distance for the thread operating on A is 3, alternative distance for the thread operating on D is 4, and they both try to write it for the distance of C. So they both execute this statement, distance of C equal to 3, and other thread says distance of C equal to 4. Which one succeeds? Anything can succeed, right? So either the thread operating on A writes first, in which case it gets overwritten by the thread operating on D, and therefore the final value becomes 4 rather than 3, or the other way around, in which case the final value is correct as 3. So therefore there is some sort of a data race happening when the two threads are operating on distance of this C node, right? So this is also a problem. This will work in sequential setting but will not work in the parallel setting. We have to ensure that this particular check and the update, the check alternative distance less than distance of n, and the update, both of these happen atomically. So there is some sort of a lock that gets taken before and that lock gets released after, right? So that is one way to ensure that this code is correct, and we'll come back to this. Okay. So let's discuss this in the context of three synchronization, in the context of three parameters. One is control and data flow. The second one is atomics, and the third one is barriers. There could be other synchronization primitives, so to say, supported in a language such as CUDA, but we are going to look at these three primarily. Okay. Let's try to implement mutual exclusion for two locks, right? So we had little bit of success towards mutual exclusion with our flag example. Now we'll make it concrete and we'll try to make it work for two threads. So one of the ways I can do it is that I can assume some initial condition which is flag equal to false, that is flag equal to 0. And then I write this code where my code again has S1 and S2, but slightly different. The question is, does this ensure that mutual exclusion is guaranteed? That is S1 and S2, they should not execute simultaneously. Is it ensured? Okay, some of you are suggesting, Sandeep, Varun, Satyabhagan are suggesting that this seems to ensure mutual exclusion. I'll wait for a few seconds for everybody to look at the code and convince themselves that this indeed ensures mutual exclusion. Okay, Pirapuraj also says yes. Shiv Prasad, what do you say? Is it ensure mutual exclusion? Yeah, Vipin, go ahead. You had a question. Yeah, Sandeep, go ahead.
Sir, I have doubt in this data structure update. Suppose if you want to update a data structure, then it is very difficult. I think it is difficult because there is a, suppose if you take a single hash map and internally it may be a red block tree and each may need a different node, but you need to, I think we need to uh, block the entire access of hash map when one thread is dealing with the entire data structure. I think it is not fair because in the hash map internally one thread may go to another node and another thread may need another node actually. So how do we handle, like, what's your call?
Yeah, so this, let's understand Sandeep's question, right? So what he's suggesting is that in several data structures, right, we can take the example of tree-based data structures or graphs, or simpler case is probably linked list. In all of these, there is a data race happening whenever there are concurrent insertions and deletions, right, as well as searches. In such cases, how do we ensure that the data race is maintained? The mutual exclusion is maintained, and not only mutual exclusion, but the important part is that the data structure should be in consistent state, right, with respect to the sequential execution. So that is actually quite a bit of a research problem, and you can always say that there is one lock available at the root or at the whole data structure level, which is called as coarse grained locking, and every thread needs to take that, then all the processing becomes sequential, right? So there is no parallelism in that. So that is not always feasible, but then there are ways in which some data structures have been programmed to support fine grained lock. What that means is that you have lock associated with each node, and you ensure that the locks are taken in a particular order to make sure that when you take a lock, well, at least that thread is that particular node is locked, and other thread should not process it. And by ensuring that these are taken in a particular order, you also ensure that there is no deadlock, etc. But this is still a tricky problem, right? So as I was mentioning, it is still a research question to ensure that optimized versions of these data structures, concurrent data structures, exist. If some of you are interested, I think this is a good topic to be researched. Since you mentioned, I'll also point you to a repository of nice data structures which might be of interest to some of you. So you can take a look at this offline. Okay, I'll come back to this discussion. So if the initial value is flag is 0, and let's say T2 executes, so it's going to directly execute S2. It's not going to look for the value, and after that it sets flag to true. And what this flag essentially indicates that which thread should go ahead, right? So flag equal to false means thread 2 should go ahead, and flag equal to true means thread 1 can go ahead, right? And depending upon that, it's going to set. So let's say that flag is actually false and T1 comes first. So since flag is false, T1 is going to wait till it gets a chance with flag equal to true. So this ensures mutual exclusion. The small problem here is that even if there is no T2, right, T1 is going to wait. So T2 has not yet come into the system. It might come later, but then T1 is not allowed to proceed because we have a fixed protocol with respect to that flag. So the question is that can we allow either of S1 or S2 to go ahead? So can somebody think of a solution to this, that if the other thread, so if let's say the other thread exists and then any one of them goes ahead and executes the critical section, that part is okay. But only one of them exists, then that thread should be allowed to enter the critical section. Can this be guaranteed, and how will you write the code for such a mechanism? Any thoughts? Okay, so towards this, let's see if this particular code works, right? So what I'm going to do is that initially I don't say that the flag value should be 0. I just say that it could be true or false. And then I have such a code, right? So where the thread 2 is going to wait as long as it is true. That means that if flag equal to 0, S2 executes. Flag equal to 1 or true, S1 executes. Does this ensure, first of all, mutual exclusion? Does this ensure that any thread which is free just goes ahead? Any thoughts? Ensures mutual exclusion but does not allow anyone to move ahead. Order will be based on initial value of flag. Correct. Sandeep says no. Yes, it enforces ordering on execution of T1 and T2. Yes, that's right. Right. So the initial value matters. Right. So as Sowmeya was also saying. So initial value does matter, and it's possible that the other thread might get stuck. Right. For example, if the initial value is false, S2 can execute. But then if T2 is not there at all, then thread 1 is going to indefinitely wait. And opposite will happen with respect to T2. But what has happened in this changed code is that now there is some sort of a symmetry between these two codes across T1 and T2. Right? So it so happens in many applications that your critical section will remain the same irrespective of which thread is executing, which means that S1 and S2 are going to be the same. And if that happens, I would probably prefer to have a single implementation of a lock. Right? So essentially, this part that we were doing is kind of similar to a lock, and this part is similar to an unlock. And we would like to now implement these such that, irrespective of which thread executes, we would like it to go ahead. Okay, there are certain assumptions that we made. One is reading and writing of the flag is atomic. Which seems to be all right, and both the threads execute their codes, right? So that was also our assumption. That is, the other thread otherwise keeps waiting indefinitely. So we'll have to come to more practical aspects now, right? So what we are going to do, and flag is volatile. So what that means is that the flag value, when it is written by one thread, the other thread actually sees it. Right? So that is also one assumption that we made. Okay. So we are going to abstract it as lock and unlock API, and of course we are going to implement that lock API for 2 threads for now. Okay, so I'm going to try that with the code that I'm going to see. Right, so both the methods should be the same, because for the critical section I need to have that, and it should use only control plus data flow. It should not use any atomic instructions or barriers, etc. Okay, so let's say that there are these 2 threads, 0 and 1. And I'm going to write this code for lock and the unlock, irrespective of what the thread ID is. What does this code do? It says that my thread ID is this. The other thread ID is, note that there are only 2 threads, right? So the other thread ID is 1 minus that, which is going to be the other thread's ID. I'm going to set my flag to true, which indicates that I am interested in entering the critical section, and then I am going to wait for the other thread to get disinterested in entering the critical section. So until then I am going to wait, and in the unlock part, and then there will be some critical section which I am skipping, and then unlock part says I am no longer interested in my critical section, in entering the critical section. So this is the code, and I would like you to think about, does this code work? The same code gets executed by both the threads. Okay. And does this work, meaning does this ensure mutual exclusion? Any thoughts? So this is kind of a generalization of the flag thing that we had earlier, where we had a single flag. Now we are going to say that there are going to be two flags, which indicate that which thread is interested in entering, and that interest I am going to check using that flag two Boolean variables. So each thread does lock, then there is a critical section which we have not shown, and then there is unlock, right? So this is how the sequence of execution is. Abhishek says flag is volatile is not required for sequential consistency because each thread threads a committed value. No, Abhishek, because it's not guaranteed that the threads will see a committed value. They might see a cached value. Sandeep says 2 may loop infinitely. Okay. Is it possible that oh, 2 may loop infinitely? Okay. So there might be, so this looping infinitely is called as a deadlock. And what Sandeep is suggesting is that maybe there is a deadlock in this. So he says 2 may lock but may not unlock. Vipin says the threads can deadlock. Right. So that part is possible. My question is, although is mutual exclusion guaranteed? That is, does it ever happen that critical section, both the threads are in the critical section simultaneously? Okay, that doesn't happen is what Sandeep says. I'd wait for a couple of responses. Okay, so Bhagavan says, okay, agrees. Is flag always false initially? Okay, that's a good question. Let's see if it is initially true for both of them. Does that change our answer? Or any combination 0, 0, 0, 1, 1, 0, 1, 1. Does that change our answer? Okay, so let's discuss this, right? So let's say the initial value of, okay, Vipin says if flag value will be overwritten, so initial value does not matter. Sandeep says yes. Okay, so let's say that the flag initial values are 0, 0, which is a reasonable case, which means actually that nobody is interested in entering the critical section, which seems to be reasonable. That seems to be the good invariant to be maintained. And whichever thread comes in, that thread says my flag is true. That means I am interested in entering the critical section, and then it waits for the other. That waiting might indefinitely happen because the other thread might never come up and so on. Right? So that deadlock possibility is there. But I am not going to enter my critical section if the other flag is 0. So I will enter the critical section. However, while I am in the critical section, maybe some other thread comes in. But as soon as the other thread comes in, it will see my modified value of flag. And therefore, irrespective of what my initial flag value is, the other thread will see flag me equal to true, that is flag of other equal to true from the other thread. And therefore, I seem to be doing fine with respect to mutual exclusion. So, yeah, we are also assuming that flag is volatile. It may lead to deadlock. If one thread runs before the other, then kind of all goes well. If they both come simultaneously and they both set flag of me equal to true, then they both are interested in entering the critical section, and then it goes like pehle aap type, and then both of them are waiting for each other. Okay, so that part seems to be good. So we would like to, and this happens because we are now having two different flags. earlier we had a simple scheme where we said that there is only one flag, and therefore at least one of them could go. Right? Now we have two flags, and that is kind of causing the issue. So we'll go back to our scheme where we say that I'm going to keep track of flag in a different variable. Let's say I'll call it as a victim. So whichever is the victim, that victim is going to be the one who is going to wait. If I am the victim, I should wait. If somebody else is the victim, then I can go ahead. Yeah, Sandeep has a question. Does volatile mean the value is committed? Yes, the volatile will mean the volatile at the language level indicates that the optimizations are disabled for that particular variable, right? Which means that every time the computation happens, the memory related optimizations do not happen, and the value is extracted from the main memory all the time, or at least the common memory, which could be L2. So that in turn ensures that the other thread will see it, right? Because you are going to write to it, and that write will not be cached, but it will go all the way to the DRAM or the last level cache. Okay, any other questions at this stage? Okay, so yeah, so we said that for primitive types, all is atomic. That part is fine. We'll call this as version 1. So I'm going to modify this version 1 to version 2, which is going to go back and use a victim variable. Okay. So what I say is that there is a victim variable, which is going to tell me who should wait. Initially, the value of victim is something, I don't know. But I'm going to set it to myself because I'm a good thread, right? I always want to give priority to the others. And therefore, I'm going to mark myself as the victim. And as long as I am the victim, I'm going to wait. Right? And then as soon as somebody else says that I am not the victim, then I go ahead and execute the critical section after the lock. And the unlock says victim equal to me. The question is, does this ensure mutual exclusion? And then what are the other properties that it satisfies? Right? Meanwhile, I'll take Soumik's question. We can guarantee that two threads will share a common cache. Then we can save some time by removing volatile. It is not possible in compile time, but can be possible in runtime. They do share the typically the L2 or the last level cache. But despite that, we cannot guarantee it. The reason being that there will always be some private memory, right? For example, L1 cache or registers, which might not be shared across the threads, and therefore, so if you keep everything shared, then you are right that volatile is not required, because it's because of the private copies local to individual threads that this issue of one update and the other one does not see it, that happens, and that can be regulated by using volatile. But yes, as you said, that if we avoid that, then that is going to ensure volatile is not required. All right, so I would like you to think about what this code does, and we will take a break. Maybe we'll discuss it, we'll sync up at maybe 10:44 or so, according to this one, so around 6 minutes from now, right? And I would like you to think about what does this code do and what all gets ensured. Okay, we'll meet up after 6 minutes. Let me stop the recording.